Well, I'd like to welcome you all to the 16th Annual Henry Kendall Lecture. It'll be presented today by Dr. Tom Karl. So I'm Ron Prynne, Director of MIT's Center for Global Change Science, which co-sponsors the lecture together with the Department of Earth, Atmospheric and Planetary Sciences, headed by Rob Vanderhilst, who I think is going to be in the audience somewhere. The Henry Kendall Memorial Lecture Series honors Professor Kendall. He was a 1990 Nobel laureate in physics, a long-time, very distinguished member of MIT's physics faculty, and a very ardent environmentalist. The Kendall Lecture allows MIT faculty and students and members of the general public to be introduced to forefront areas in global change science by outstanding researchers. Henry was a founding member and past chair of the Union of Concerned Scientists. He played a leading role in organizing a number of very influential scientific community statements on global problems, including the most well-known one as the World Scientist Warning to Humanity in 1992. That is copied in the brochure that you had in the second half of it, and the call for action at the Kyoto Climate Summit in Kyoto, of course, in 1997. Today's lecturer, Tom Karl, has had a long and very distinguished career in the National Oceanographic and Atmospheric Administration, known as NOAA for short. He was a senior scientist from 1992 to 1998. Then he became director of the National Climatic Data Center from 1998 to 2015, and then director of the National Centers for Environmental Information for 2015 to 2016. He's now seems to be very happy in his retirement, and that's why I think we were able to get him here. Tom Karl has certainly served the nation in what I'll call interesting times in inverted commas. During his 1998 to 2016 term as a director within the NOAA system, the world witnessed the 12 highest global annual average temperatures ever recorded since 1880. Tom was responsible for delivering that dire news to a not always receptive Congress. Tom received his Bachelor of Science from Northern Illinois University, his Master of Science from the University of Wisconsin at Madison, and a Doctorate of Humane Letters from North Carolina State University. Tom is a world authority on quantitative studies of climate change in the United States and globally, as recorded in a vast array of atmospheric, terrestrial, cryospheric, and oceanic observations from surface, submarine, airborne, and satellite sensors. He has his arms around huge amounts of data in his job over these many years. His many research accomplishments are described in over 200 peer-reviewed articles and books. He chaired the United States Global Change Research Program Subcommittee on Global Change from 2010 to 2016, in other words, through the Obama period, and was responsible for the delivery of the Interagency Global Change Research Plan, climate assessments, and annual reports to Congress. He was also chair or lead author of the first three of the U.S. National Climate Assessments and has testified many times on climate science before the U.S. Congress. He served as president of the American Meteorological Society and a member of its executive committee from 2009 to 2012, and he served as editor of its premier Journal of Climate from 1998 to 2000. Tom has also contributed substantially to major international organizations in climate science. He served as lead author, convening lead author, and editor on the first four Intergovernmental Panel on Climate Change assessments, or IPC as they are called, from 1990 through 2009. He led the U.S. delegation that approved the 2014 fifth IPCC assessment on the physical basis for climate change. Tom Carl is a recipient of a significant number of prominent awards, including the American Meteorological Society's SUMI Award, the Presidential Rank Award, 6 U.S. Department of Commerce gold medals, and the Helmut Landsberg Award from the American Association of State Climatologists. Tom is a fellow of both the American Meteorological Society and the American Geophysical Union. It's my pleasure to welcome Tom to MIT today. Title of his talk, as you can all see, is Climate Data, Mysteries, Wonders, and Reality. Welcome.
Thank you, Ron, and it's a very great honor to be here and to talk about one of my favorite subjects, climate data, to both those who participate in the Global Change Center for Global Change Science and with the Earth Atmospheric and Planetary Sciences program with the department. I have only several hundred slides, so I'll have to get through this pretty quickly. But I do have a fair number of slides, but there's not a lot of content to some of them, so hopefully I can get through this and you'll be able to understand what point I'm trying to make here. But first I thought it would be important to give an appropriate context because we're dealing with really the mysteries, wonders, and reality of climate data. And so here's a little cartoon. For those of you who are fans of Don Quixote, and maybe I, in this presentation, consider myself kind of the Don Quixote, talking to Sancho Panza. Sancho, you consider yourself fortunate as I've deemed you worthy to accompany me on wondrous acts of chivalry, conquest. You'll see places of grandeur, noble adventures, deeds of bravery and courage beyond your wildest imagination. Sancho says, I believe everything you say, your worship, but right now you might want to buckle your saddles. It seems to be slipping off your high horse. So the point here is that while there is a lot we can do with this climate data, but as you see, there is a certain amount of reality to it. It is amazing today if you consider what information we have to draw from all the different observing systems, from remote sensing, satellites, subsurface measurements in the ocean, land weather stations, upper air stations, radars, satellite imagery, and that's not to mention the data that comes from models. An enormous amount of information to pull together to try and make sense of what the state and changing state of the climate is. The wonders, it is amazing. Quality is remarkable when you think about the kind of measurements we're getting today, the variety of measurements, have you seen from that previous figure? The volume. I tried to make an estimate as how much of climate data is in the major centers around the world today. And an exabyte is not an exaggeration. That is a lot of data. Put some context on depending on how big your personal computer is. And that's about 1 million personal computers. The measurements we have, active measurements, passive measurements. We've got international cooperation and data exchange, not to be underemphasized, because without that, we would not have nearly the amount of information we have today. We've got 24 by 7 by 365 and 366 in a leap year measuring going on. All this to not only predict what the climate's going to do, but to document where we are now and how the climate is changing. So it's a remarkable set of assets that we have to draw from. Now, I said we've got great quality. We also have tremendous diversity in the quality. And so this then leads us to the reality and a lot of discussion amongst climate scientists as to how good is this data anyway. Here's an example. This is a reference climate reference station that has been set up specifically for the purpose of measuring climate variability. I'll talk more about this and how we use it, but you can look here. There's a number of independent rain gauges in the middle of this double fence to try and protect the instruments from aerodynamics effect, the precipitation gauges from wind. It's got 3 aspirated sensors, platinum resistance thermometers, extremely good. But we also have many stations to draw from that don't have this high quality. And here's the worst example that I think we could find. This was a picture of a NOAA cooperative weather station. And you can see here's the cooperative temperature measurements being taken in this instrument shelter 5 feet away from this trash burn barrel. So the question is, well, how do you make sense out of these data? Can you really trust them given this disparity? We have issues of quality that relate to the calibration history of the data. So in other words, I want to know how those instruments have been maintained over the years. There has been changing in observing methods, the way in which temperatures, for example, are sampled or precipitation sampled. I need to know that. Changes in instrumentation. How good is the metadata about these types of changes? Can I trust it? That's also extremely important. The environment surrounding the measurement, is it changing over time? Has that burn barrel been there forever, or has it just been reintroduced in the last couple of years? How do I interpret the measurement, the meaning of the measurement? Is it in an urban environment? Is it in a rural environment? Is it in the free atmosphere? All important. And then, not to be dismissed, if I'm going to make measurements, do I have power available? Is it solar power, some way of making an active measurement instead of a passive measurement? Do I have capability of bringing power to my measurements in remote locations? Those are all important aspects, mysteries of really trying to understand this data that one has to consider. What I'm going to try to do to bring some reality to looking at this data is look through a couple of examples. One is constructing time series of changes in global temperature, and in particular focusing on this so-called pause in global warming that's been talked about for the last number of years, particularly since the IPCC 2013 report. And also want to talk about measuring precipitation and its change, how much, how fast. We'll have some examples there and go through some of the issues. So I put this picture here, and I know some of the authors of these papers are in the audience. I know I saw Kerry Emanuel here, and I think he was part of one of the set of the co-authors. I put this on just to give you a sense of where we think we are when we talk about changes in temperature and precipitation. This diagram was put together by about 50 experts looking at whether or not we had more knowledge or less knowledge regarding a set of extreme phenomena that you see here. Everything from ice storms to heat waves, extreme precipitation, cold waves, and everything in the middle. So how much knowledge did we have with respect to our ability to detect changes from an assessment of 50 experts? And how well did we understand, if we saw the changes, the causes of those changes? Not unsurprisingly, there seems to be a relationship. Our ability to detect changes is related to our ability to better understand why those changes are occurring. So if you don't have much information of being able to detect changes, you don't know much about the causes of the changes. So we're going to talk about temperature, and certainly heat waves and cold waves are part of that, and precipitation. And you can see these are in the upper part of the diagram. Droughts, obviously, lack of precipitation, also related to the upper part of the diagram in terms of more knowledge and our ability to detect. So you'll see some of the problems that I'll talk about in these quantities, and so you can contrast to where we might be if we be talking about what do we know about changes in thunderstorm winds or changes in ice storms. Not very much in contrast. So I said we'd talk about temperature first, and obviously a lot of interest in global temperatures. Not surprisingly, because there's a lot of interest in what humans might be doing to global temperatures. And here is the interesting relationship, global carbon dioxide concentrations plotted against global temperatures, not to imply a one-to-one relationship, but certainly raises one's eyebrows. This temperature measurement goes out to 2015. If I had 2016 up here, which you'll see in some other figures, it's even a little bit higher. Now, you can look at this picture and see temperatures a bit unsteady in the middle part of the 20th century. But since about 1970, the mid-70s, if you stand back and look at this, see the temperatures have been rising rather unsteadily, I guess is the way to describe it. You can see 2015, 2016 beat 2015, and where we are now in 17 is in that same ballpark. And so if you were just simply to look at the trend of temperature from 1998 to 2016, it's 0.17 degrees C. Here's a simple linear trend, and you'd say, well, not much of a hiatus there. If you take a look at another set of years, 2002 to 2009, there's actually no change in temperature. You can see that by this black curve here. These are for global temperatures. And so you might, if you had no knowledge of what happened to the right here, look at that period and say, well, gee, are global temperatures now at the point where they stopped rising? Do we have the correct information as to what the cause is? And there's another way you can look at the change in the slope of time series. You can do a little more robust statistical analysis, something called empirical modal decomposition, which doesn't pretend any particular shape to the time series. And you can see from 1880 to 2015, when this analysis ended, various slopes, instantaneous slopes. And you can see since about 1970, the slopes have been increasing, but they do vary over time based on this analysis. You can go back to the simple trend method, 2007 to 16, say the last 10 years, rates of warming, 0.3 degrees C per decade. Last 15 years, 0.17, 25 years, 0.19. So clearly positive changes, but you can find, as I showed you, from 2002 to 2009, period where global temperatures aren't changing much. Now, what happened a few years ago when IPCC came out in 2014, there was an interesting discussion about the changes in temperature, and I'll point to this period here, the so-called hiatus period, 1998 to 2012. So IPCC had that period to look at. You'll see two symbols here. A circle is the data set that was delivered by NOAA to IPCC, one of 3 data sets that were used to look at global temperatures. And you can see the rate of warming was positive, but the error bars, these are 90% confidence intervals. That's what IPCC used. went below no trend at all. And what happened subsequently in 2015, we had to do some corrections to the data because of a systematic bias, which I'll talk about in a bit. And when those corrections were applied, the rate of warming was significantly higher. And one could make the case, well, there really wasn't a strong case for a hiatus once those corrections were put in. This has led to many, many research papers talking about whether or not the data is appropriately corrected, and can we trust this revised data set, and what about some of the other data sets. Now you see there's a number of other symbols here, and one thing I want to point out, you can go look at this period here, 1998 to 2014, slightly different than the 2012. This is again for global, but what you see here is this triangle, and what was done here was, in addition to a set of corrections to primarily the ocean data, there was a method of trying to estimate what was happening in the Arctic Ocean, the changes in temperatures over the Arctic. And when that was included, the rate of warming was even larger than what was reported with the corrected data set or the previous version. So if you look at this data set over with the Arctic warming included, you'll find the rates of change between this line, this symbol, and what you see from 1951 to 2012, virtually indistinguishable. So you can decompose that, what's going on in the ocean, what's going on land, and I'll go through some of the corrections that the data was subject to try and get to these revised rates of warming and how they compare amongst various global data sets. One thing that happened shortly after the IPCC in 2014 was the update of global land surface temperatures that were used to calculate changes in land temperatures. And you can see in this data set, which was updated in 2015, the number of years available for each station, and not surprisingly, you can see over North America, much of Europe, and a good part of the Northern Hemisphere, considerable number of stations with over 100 years of data. The red dots in the Southern Hemisphere are much more scattered. But this was an enormous improvement in the amount of data available to calculate changes in temperature for the globe. And to show you what this looked like, the number of stations that were available, here plotted in black was the previous version. These were the number of stations that the IPCC was drawing from because that's what was published. When you look at this new data set, you can see an enormous increase in the number of stations available. That's extremely important because one of the things you want to do with these stations is not only increase the spatial coverage, in other words, measure changes in places around the world as best representative as you can of the whole global landmass, but to try and identify potential errors in the data, like what we showed you, with that one cooperative station compared to the Climate Reference Network, you want to contrast and compare stations. So there's a number of analyses that do pairwise assessments of whether or not a station in one location is consistent with the changes in a nearby location. So the more stations you have, the better off you are in beating down that uncertainty. Now, although there was a lot more stations, this is the percent of the land area that was sampled. And you can see in the previous version, there was this decay after 1980. Not that there wasn't stations recording, but scientists hadn't made a concerted effort to go and collect these data from all the countries who had them available in their national archives. And this effort, the International Surface Temperature Initiative, number of dedicated scientists had made that effort to update the data set. And you can see now the land area sampled was substantially improved, and you don't see this large decay in the last number of decades. Especially important because this is the time we were talking about, is there a hiatus in global warming or is there no longer a hiatus? So one of the things that's important to do is to compare and contrast different methods to construct global temperatures. And what that enables you to do is to see whether or not the approach that different groups use to correct for errant values and changes in calibration, sampling method, landscape changes, whether those differences give you profoundly different results. And you'll see here in red, this is the current NOAA land data set that's in use today. There is a new version that is still in review, but was made available online. The latest version, you can see it's in black. It's hard to see a lot of difference. It's almost indistinguishable. There's another group out at Berkeley. Zeke Hausfather is leading that effort. You can see the blue line here showing slightly warmer temperatures in the last couple of decades compared to the current NOAA land data set. And then there was a data set that my colleagues and I put together in a science paper called the Carr et al. Land data set. It's not being updated. It ended in 2014. It was only slightly different in terms of trends compared to the current version that NOAA is using. So you look at this and you say, well, there are differences, but certainly not spectacular, and the more recent versions show somewhat greater increases in temperature. Why might that be? Well, I'll spill the beans in large part because there's more coverage in the high latitudes. And you'll see later where the warming is greatest is in the Arctic areas. And that now is being better sampled. So I just want to go back and say, well, how, you could compare and contrast different groups putting together data sets, but can you compare it to reference data? And in the US, this is a reference network that has been operating now since 2001, but really since about 2005, 2006 is the time frame where all these stations have been operating, and it's still expanding up in Alaska. And there's a number of sites in other countries for comparisons with their measurements. But this network was ideally put in to really measure multi-decadal changes in temperature. And so we can look at this network and compare to what we would obtain if we had longer records, but not of as high quality. And here's an example of what we see in the Climate Reference Network. I already mentioned there's a number of precipitation gauges, a weighing precipitation gauge, a tipping bucket. There's a double fence to protect these gauges against the aerodynamic effects of wind, which can really affect how much precipitation you actually measure. There's 3 thermistors here. These are platinum-resistant thermometers, and they're all aspirated. There's an anemometer at the height of the fence to try and ensure you know what the wind speed is if there need to be corrections for aerodynamic effects. There's a whole sorts of additional measurements that can help better understand what you're seeing in the temperature measurements. The value of having 3 sensors, here's an example. Sensors do go bad. If you've got 3, it's pretty easy to find out you've got a problem and which one it is. And this has been used to go out and fix these sensors. So the point is you really got a great network here. Here's examples of the pictures. You can repeat those photos year after year to make sure there's nothing unusual going on with changes in land use that could affect the measurements around the station. And if there is, then you can try to account for that. So again, going back, we can compare, how does this, now this is the worst example. Many of the other network sites in the regular weather observing and climate observing stations are not nearly this bad. So I'm giving you an extreme example here. But there are problems in those data that one tries to correct for a priori. And a simple thing is, you saw that instrument, I'll go back to it, someone has to go out in that box and either look at the measurement, or there's another system out there called the maximum minimum temperature system. Someone has to push a button, and what it gives them is the measurement of the maximum and minimum temperature for the last 24 hours. Well, that's great if you always go out and measure the temperature at the same time every day. And people did that. Normally, in the middle part of the 20th century, they did that in the afternoon, usually around 5 o'clock in the afternoon. And what happened is the number of afternoon readers, or late afternoon is really more appropriate, evening, slowly declined over time in favor of people going out in the morning and making a measurement. The hydrologist said, we really want to know what the rainfall is in the morning. Can you go out and measure your rainfall and your temperature in the morning? And so there's a concerted effort, and observers went out in the morning. Now, when you do that, you introduce a bias in the temperature measurement. And we can test that. You can actually go and look at stations that measure temperatures on a 24-hourly basis, and you can pretend as if you're measuring the max and minimum temperature at different times of the day. And you can see if you go out at 5 in the morning, you are colder than the person going out at 1 in the afternoon, or 4 o'clock in the afternoon, 5 o'clock in the afternoon. So what was happening in this network is a switch from morning observers to, from afternoon observing to morning observers, introducing a cold bias. So you have to correct for that. You can develop a model to do that. Here's an example of what those biases are after you apply the model, and you can go back and test the model. You can see it's not quite perfect at noon, but since most of the observers here are going from 5 o'clock, from 7 o'clock, the model is actually pretty darn good at that time. So that's an important example of a correction that's applied to these data. Then you can actually compare and contrast a data set. This data set here is US HCN version 2. They're now on version 3, and there will be version 4 with even better improvements. And you can compare that to this climate reference network with all those red dots across the US and calculate the mean annual temperature and see how different they are over this time period. This figure ends in 2011. You can see they're not terribly different. And in fact, I've got some additional slides showing this trend going out even further. A recent paper by Housefather, published in GRL. This is looking at max and min temperature differences between the corrected historical climate network data and this reference network data and the uncorrected data. And you can see there are some differences, but what you see is a slow decrease here, meaning we still probably are over or under correcting the maximum temperatures, There's a built-in warm bias in the data for the maximum temperatures. The minimum temperatures look pretty good. And you can see the corrections actually bring this down a little better, the red a little bit less than what the blue is toward the end of the series. So we know there's probably still some bias left in this data. This analysis suggests, at least over the US, the maximum temperatures are probably warming a little bit more over these last 10 years than we have been reporting. Here's another way of looking at it. Unfortunately, this is the one slide that the color didn't show up. If you look at just all the pairs of stations, this is for the uncorrected data, and you can see differences between the pairs with the climate reference network. They're negatively biased, and they're pretty wild at the tails. You correct the data, it narrows up, the bias gets decreased. And if you just look at pairs of the climate reference network, they center around 0, and they're even narrower. I know that's hard to read. The point here is, after this analysis, you're pretty confident that you're getting the US data reasonably correct, although, as you saw in that previous diagram, there could still be some small bias in the maximum temperature. Turning our attention to sea surface temperatures, we have a variety of ways to measure sea surface temperatures, particularly if you want to go back in time, from buckets, from wooden buckets, canvas buckets, and these have different issues associated with them in terms of, in rubber buckets, how water evaporates from these if you pull them up and stick a thermometer in them. What has been a really remarkable improvement in our ability is we got many drifting buoys measuring temperatures across the ocean. We've got moored buoys that have been put in, and more recently these autonomous profilers that go deep into the ocean, giving us yet another way to look at ocean temperatures. If we take a look at how this has changed over time from 1950 to present, what you see is the drifting buoys have grown remarkably in the number of observations. The moored buoys have grown, but not nearly as dramatically. And the ship observations have actually decreased a bit, or stayed the same since 2000, but decreased since 1980. So what you're seeing is a changing mix of observations to measure sea surface temperatures, and one has to be very careful how one treats that. Why? Because if you actually look at the sea surface temperature anomalies relative to the device that was used, if you look at the buoys in red here, this is the red line. It's only plotted since the late 1980s because, again, the buoys came on pretty strong here in the 80s. This is the red diagram up here showing the fractional contribution to global average SST. You can see the buoys grew proportionally larger than any of the other methods, and they were colder in contrast to the ship temperatures, these hull contact sensors measured from ships. And we still had some bucket temperatures being used, and you see they're slightly warmer than the buoy measurements. You can combine them all, that's what was done in the IPCC report that NOAA's data contributed to, and you can see that black line. Well, clearly, if you're going to combine data that's increasing over time and is cold, you're going to introduce a bias, and you introduce a cold bias. And that's what we had to correct for in the analysis, among other things. So when that correction was applied, the hiatus largely disappeared. There's an example of the coverage of the drifting buoys. This is from March 6, 2017. You can see not only do you have more observations, but they're in places where traditionally ships were less frequently available to contribute to the global SSTs. So a major advance. Put this diagram up because I just wanted to point out when you correct the data for these different mix of observations, The biggest corrections are in the late 19th century and early part of the 20th century. This is the uncorrected data, this blue, listed from ICOEDS, a data set. And what we actually do is when we correct the data, we actually make the rate of warming less than it might otherwise be. The largest correction by far is to reduce the rate of warming. Certainly I talked about these corrections over here. They're small in comparison to these huge corrections in the earlier part of the record. Now, what is really important, as we mentioned earlier, is the idea of having independent measurements to try and look at whether or not one is getting anything comparable amongst the data sets, or if there's an outlier. And here's a paper that was published by Hausfather in 2017 in Science Advances. And here's the so-called old NOAA data. This was the data that was used in the IPCC fifth assessment report. And you can see it is an outlier among these other data sets. This is a data set of buoys only. And here's a data set independent from satellites only. Here's the new NOAA data, the red one, and you can see the linear trends on these things. So we have a lot more confidence because we've got drifting buoys, we have Argo floats that measure temperatures near the surface, and they're in much closer agreement with this new revised NOAA ocean data that was put out recently compared to the old NOAA data. So what it does tend to do, it makes that hiatus much less apparent. Still, you can find it, as I showed you with the 2002 to 2009 time period. You can find periods of not much warming, but certainly less apparent when you correct the data. There's a new version of the sea surface temperatures that NOAA is working on. It's ERSST version 5. Here's a preliminary version from Peter Thorne, who's working on that. And all I can say is it's virtually indistinguishable from the previous version. And in contrast to the two other data sets that were used in IPCC for the sea surface temperatures, they're slightly cooler, especially in the recent time periods. One important reason for that with respect to this Hadley data set is, and you'll see in a second, the spatial coverage, the fact that the approach they use is to be very conservative and not estimate temperatures where they don't have data. And that may be fine, except when you've got parts of the world that are warming fairly dramatically. Here's another example of global temperatures. This is from a reanalysis from a model. This is an example of taking all the information we have from all those observing systems that I showed in the early part of the talk, trying to use our understanding of the physics in the climate system to come up with a surface temperature. And as you can see, this analysis, which ended in 2015, shows some fairly consistent warming like the observational data in the last few years with some very high temperatures. So I mentioned earlier what was part of the reason that the sea surface temperature data from the Hadley Center isn't quite as warm as some of the other data sets. Cowaton and Way published a paper on global temperature trends this is from 79 to 2002, and they showed when you actually estimate, they used a kriging approach as a statistical method to estimate changes in temperature over the areas where there aren't many observations. Substantial warming, this is being left out of the Hadley Center data in the spatial analysis. And in fact, if you see what was used in IPCC, 1901 to 2012, a lot of blank areas. This is the NOAA data where there is more extrapolation. This is the NASA data. They actually make a concerted effort to try and figure out what's going on in the Arctic. And so you can see part of the reason for the differences amongst these data sets is how they're treating data that's not available. And when data comes in, even today, despite the fact that we know the Arctic is warming strongly, some of the analysis don't incorporate it. And I can tell you one of the things that we've seen that's really tricky, when you actually look at some of the land stations in the high Arctic areas, you put quality control analysis schemes. If you get a 5 C difference between normal climatology in any given month, that data gets kicked out. Well, what we've seen in some of these areas, when there's no ice now in some of these locations, they can be 5 C warmer. So I have to go back to these quality control programs and change what we were throwing out before as being bad and now keep it, just because the sea ice has melted. The ocean allows a lot more heat to escape into the atmosphere. Temperatures are much warmer than they might otherwise be had they been completely surrounded by ice. Another issue that has come up, this is from a paper from Calton and Way and others, and that is making sure if you compare models to observational data, you compare apples to apples. The red line shows an example. If you only look at the surface, 2-meter surface air temperature, both over the oceans and the land, you get this red line, significant warming. These are from the latest generation of models averaged together. However, if you look at the fact that how our global temperatures are calculated, we use sea surface temperatures and land surface temperatures. Sea surface temperatures aren't warming as fast as the 2-meter temperatures, then the models don't show as much warming. If you now mask the models for the same areas of the globe that you have observations for, the warming even gets smaller. And you can see these differences are fairly substantial. So you have to make sure, the observed here is the gray. You have to make sure you're very careful in what you're comparing and contrasting to see if indeed there's any consistency between what's observed and what might have been expected from models. And here's an example using that correction for comparing apples to apples. These red and blue lines, here's what all these models suggest with business as usual kind of scenario for increases in greenhouse gases. And if you actually update the forcings that we've seen beyond greenhouse gases for volcanic eruptions, solar variability, you can see the observations and the models are much closer together. So I've talked a lot about the in situ measurements, but not much about satellites. We've got a number of methods to take satellite data and incorporate buoys and sea ice to come up with an optimally estimated product that has both satellite data and measurements from the ocean. If you do that, you can see you get rates of warming between 0.07 and 0.15 per decade, 1982 to 2014, depending on the data set you use. And the key here is the outlier in this is our old ocean temperatures, where we know we had a bias with respect to the way we corrected for the drifting buoys, and this optimal interpolated SSTs from satellites, when we recognized there was a problem of seeing and mixing up very light cirrus and interpreting that as sea surface temperatures, actually making the SSTs too cold. We then actually ended up with a bias. In fact, we stopped using this product and went to this daily approach where we corrected it for the ocean temperatures made from buoys and ships. You can compare this. This is a set of analyses from the Argo floats, the buoy floats, a number of different ways of doing the sea surface temperatures from satellites. And you can see the odd one out again is our old NOAA data. The new versions all have substantially warmer temperatures. Here's an example. Zeke Hausfather published, as I said earlier, another example of that analysis with the new NOAA data, the Berkeley data, the Hadley data, the old NOAA data, the NASA data, the count and weigh data. And you can see, again, here the two outliers are the old NOAA data and perhaps the Hadley data set in purple. So I think we have a lot more confidence that the hiatus that was reported is not nearly as strong as we thought, but you can be the judge because there is a lot behind these data. One thing that has also been talked about, not just the surface temperatures, but what about the tropospheric temperatures? What can satellites tell us above the surface? Does it give us a consistent figure? And there's always a trade-off here. You know, you can try and use geostationary satellites, but they only cover one part of the globe. So polar orbiters have been really the go-to satellite, and particularly the microwave measurements on polar orbiters. There's a lot of issues with satellites. In fact, Carl Mears, who's probably the world expert on this, has said, you know, he thinks it's more difficult to correct the satellite data for temperatures than the in situ data. You have orbital decay in different fields of view, gaps in measurements. You've got inter-satellite temperature differences, and they actually vary when they're over land and the ocean. You have orbital drift. We have our old observation time bias problem, instrument degradation, and we have to understand what the heck we're measuring. We'll talk about that in a second. From the microwave sounding unit, there's a number of weighting functions that can be used to look at measurements in the troposphere. And depending on the way you use these channels, these microwave channels, you can get different weights, and they emphasize different parts of the troposphere. There's been an effort to get at the lower troposphere. There's some issues, obviously, with how that works over very high terrain. There is measurements here from the satellite that there's a channel here called T2, but you notice T2 goes pretty high up into the stratosphere, and we know the stratosphere is cooling, the troposphere is warming, and so you might get a mixed signal here if you're really trying to look and see how much warming has occurred. So there's some clever things people have done, do some linear combinations of different channels to try and get an improved weighting of the troposphere as opposed to having this slop into the stratosphere. When you actually do that and make some of the corrections, here's an example. Here's the mid to upper tropospheric temperatures that's been corrected. You see a warming, 1979 to present. Here's the uncorrected temperatures. The warming is not as strong. And here's an example over the tropics. Now, I mentioned observation time bias. Here's an example of the changing time in which the satellites cross the equator. And you can see some satellites have drifted a lot more than others. This actually introduces significant bias. Here's an example from Carl Mears and Frank Wentz showing that observation time bias, depending on the local crossing time of the satellite, derived from global models. These are from a climate model, but not trying to predict into the future, but just looking at what would the impact would be if I cross the equator with a satellite at different times. And so they go through their data set and try and make an adjustment. When they make that adjustment, here's the global temperatures in the middle of the troposphere, 80 south, 80 north. And you can see you get substantial warming. Now, here's a similar diagram for the tropics. Now, if you actually look at the differences, as we said, it's important to look at different observing teams. University of Alabama at Huntsville, John Christie and Roy Spencer has a data set. So does NOAA has a data set from STAR. And this is the difference between the Mears et al. Data and the other two data sets. And you can see some substantial differences with the University of Alabama data set, and not nearly as many differences with the NOAA data set, except the more recent years. So clearly there is still some work to be done to try and understand what the cause of this difference. These are totally different approaches that are being used by these different groups. I just wanted to show this diagram, again showing even with the satellite data, strong warming you see in the high latitudes, therefore important to consider what's happening in the Arctic if you want to have a good estimate of changes in global temperatures. We also have weather balloons. This picture is from IPCC showing changes in temperatures from 79 to 2002. A bunch of different groups putting together different estimates of radiosonde changes or changes in temperature from radiosondes, weather balloons. You can see warming in the troposphere curving over to cooling in the stratosphere from the weather balloons. If you look at the satellites, a similar kind of a picture, of course, varies from data set to data set. So I wanted to talk a little bit about precipitation. We've got enormous number of satellites up there that can help us with precipitation, in addition to the in situ measurements. Again, here's where we are with precipitation relative to some of these other phenomena. Now, when you talk about precipitation, it's great. You have satellites, we've got radars, we've got gauges at the surface, we've got models. They all have, in green here, some really wonderful attributes. Satellites, global coverage; radars, high spatial resolution; gauges, it's actually a direct measurement, a long history; models, a global average that are really linked to the physics, chemistry, thermodynamics. The red is some of the things that are not so desirable. Indirect measurements, except now we do have some flying radars, which is a little more direct. Viewing angles, issues, orbital changes, the hydrometer type, the size distribution of the rain droplets. For the radars, we've got biases with respect to signal strength, attenuation, different operating methods. With respect to gauges, single point, that's a real problem, particularly when we talk about how are we going to compare these measurements between themselves to try and find out which is correct or which is an outlier. And with respect to models, a lot of issues with respect to how you interpret these data. I mentioned a number of these things already. We'll go through some of the in situ issues. Fortunately, we have a number of experiments that are going on where people try to intercompare precipitation measurements. Here's an example, particularly looking at solid precipitation, a Swiss Alp site. Good set of measurements from various ways of looking at solid precipitation. Different gauges from tipping buckets, the radar, a dysdrometer, shielded snow water equivalent measurements. And you can see substantial differences. These are accumulated precipitation throughout. This is from 2013 all the way through 2014 in June. And so one has to be very careful if one is looking at changes in precipitation, and they're coming from a changing mix of these measurements. Here's an example of how wind speed, it's 30-minute average wind speed at the bottom. Here's the 30-minute accumulation catch. Looking at one instrument, the weighing gauge is a popular gauge, but 3 different sites. And you get tremendous differences in the biases, largely due to the amount of solid precipitation you get at different sites. So I'm giving you a picture, a lot of problems with precipitation, many of which we haven't been able to deal with. Why is it important? Well, if you look at projected changes, here's an example from some of the IPCC models. This is from the generation that was used in the IPCC 5th assessment. This is from the the National Climate Assessment, the U.S. National Climate Assessment. You can see fairly dramatic expected changes with high emission, more precipitation, high latitudes, and it varies by season. If we try and have an estimate of what we see in the data that we've used to calculate changes over the last 30 years compared to the first 60 years of the 20th century, you see some rather interesting characteristics, increases in the fall, precipitation, mixed bag in wintertime, and some significant increases in the spring. Is this data real? Well, most of the gauges here have been the typical gauge that the National Weather Service has used, which hasn't changed too much for a lot of these stations, but some of them, they have changed. These have not yet been corrected. So there could be some nuances here that are important. Here's what the changes look like across the contiguous U.S. You can see considerable decadal variability, but substantial increases in the last few decades. All kinds of issues with the in situ measurements. Globally, there's really no standard design. The precision and measure and accuracy of the tipping bucket measures, these measurements vary greatly, and that tends to be the most prevalent. Calibration procedures change from country to institution. The environmental conditions around the gauge orifice, we don't have good metadata on that, and that's important with the aerodynamic effects. So a lot of issues associated with precipitation, least of which is how do you compare what is measured from, say, a whole suite of rain gauges to a model observation. And the model observations are in a grid cell. And so here's an example. Francis Weirs sent me this picture. They actually had 40 in situ rain gauges inside a 50 by 50 kilometer grid. This is up in Vancouver area. And you can see when you compare these, the model and the observations, the black and the blue don't look too much different. But there are very few places around the globe where we've got 50 or 40 stations with a 50 by 50 kilometer grid scale. So some real issues of how we're going to compare and contrast these things. Other people have looked at satellite-derived data, a whole bunch of teams looking at various ways to look at satellite data. And one can also compare that to radar data where we have it at the surface and gauge data. And if you make that comparison, this isn't even looking at changes. This is a paper from Kidd et al. This is just looking at, can we figure out what the mean precipitation is? And you can see, depending on the method, you get substantial differences. Now, when you look at changes over time, this is for southern England, where we do have a very dense network of gauges. You can see the gauge data here in the dotted, kind of down here at the bottom. You can see some satellite estimates, this Persian data set, way, way off. If we look at the ECMWF, or reanalysis data, tends to be more precipitation than what we see from the rain gauge data. So we have a lot of work to do with precipitation. There is hope on the horizon. The GPM, Global Precipitation Monitoring Satellites, these are essentially flying radars. Combined, you can actually now, with this iMerge data set that NASA's putting together, it's updated every half hour. We have 12 different satellites. I'm sure there'll be a whole host of other issues, but at least this is a new attempt at trying to get global estimates of precipitation. Here's what we come up with from IPCC. Not much evidence for strong changes in global average precip. This is the global average, a number of different groups putting together the data. You can see more variability here from group to group than what we saw with the temperature measurements. And you can see part of the reason is we just don't have the measurements except more recently here, the 1951 to 2010 period. This is from IPCC. There might be some hope with the extremes of precipitation because with the extremes, they're not affected as strongly by the aerodynamic effects of wind unless they're coming during hurricanes, which in some places of the world, that certainly occurs. But the expectation is extremes of precipitation are going to go up, and here's, in fact, one algorithm that includes water vapor into its algorithm, and with increased water vapor, some pretty spectacular increases in extremes of precipitation anticipated. Here's what the models are predicting. The heaviest events get heavier, the lightest events get lighter. And you can see the sensitivity in some of the climate models to global precipitation. 20-year extremes, the scale here goes from 0 to 50%, much more sensitive at the extreme for a given rate of global temperature increase. Global increases of mean precipitation, much smaller. Here, this is only 2% versus here up to 10%. And here's examples of what it looks like spatially in some of the models. So one will want to be able to measure changes in extreme precipitation, not just globally, but spatially, because there's a suggestion of important differences. And there's a lot of interesting reasons for this. If you look in the models, the changes in vertical velocity, you can see along the equatorial areas, the tropics, increases in vertical velocity. But if you look at precipitable water, large increases in precipitable water in the high latitudes, particularly in the North Polar regions. And you can look at precipitable water differences in these models, and you can see that there are preferred regions. This is 60 to 90 north in the dark green areas where precipitable water goes up substantially. If you look at the southern hemisphere, there are increases, but they're not nearly as strong. So a lot of texture there. If we look at what we think we see in the observational data, here's the observed change in extreme precipitation, 20-year return periods, 1948 to 2015. You can see they are increasing in most of the U.S. and in some areas rather dramatically. This is over 0.4 of an inch, sorry for the change in units, in the southeast part of the U.S. in the fall. But you see almost every season has increases in extreme precip. So in conclusion, now you've seen the mysteries, the wonders. Don Quixote would say, my judgment is clear, it's unfettered, the dark clouds of ignorance have disappeared. But the reality, Sancho says, I sometimes think all you tell me is windy blather. Clearly, there's a lot more to be learned here, but I don't think we can say we don't know anything. We know a heck of a lot, but there's still much more to learn. So, thanks.
Tom would be delighted to answer questions. To enable the audience to hear the questions, if you are able to get up and use the microphones that you see set up here in the alleyways coming down, or if you can shout very loud, that's the alternative. You are all convinced that what Tom said is correct?
Yeah, I'm convinced it's correct. I'm just seeing the large oscillations that aren't periodic and must have a cause that's built into models somehow. I'm just wondering what some of the possible explanations are from things that have happened in the last 50 years. Are they events, or are they slow changes, or do we know?
Well, I think clearly there's a lot of factors that are operating on global temperatures. One example that we probably understand as well as any of them is the effects of volcanoes. And in fact, in IPCC, the 1990 report, and there was an interim report in 92 that was put out, Mount Pinatubo had erupted, and there was actually a prediction that the global temperatures would decrease, and the prediction was pretty darn close to right on target. So there's certainly some things in the global climate record that we can actually see and predict over that, span a few years, and we think we have a pretty good handle on. The other ones, like changes in greenhouse gases, accumulate over time and are affected by, as I mentioned, volcanoes and natural variability. So I think part of the discourse that we've heard with the global temperatures is the fact that they do have this ongoing forcing from greenhouse gases, but they're being affected by other characteristics. We know that the ocean temperatures themselves have some cyclical behavior. Depending on which basin you look at subsurface ocean temperatures, there's accumulation of heat. So there's a lot of factors that operate on global temperatures, and they can appear in some places to look like they're oscillating behaviors.
During this last year, there was an event where somebody was threatening to sue or did sue and enlisted all the big tops of all kinds of different government agencies. And a friend of mine who's a former LLNL scientist, a weapons scientist, but said that all of a sudden the blue skies of his childhood were there, and he just hadn't seen them for years. Did that make any sort of strange spikes in any things that were being observed at that period? Within this last year? Could you comment in general on chemtrail-type operations, or is that a taboo subject?
I'm sorry, which operations?
Can you comment on HAARP or chemtrail things or any of these things that mess with our atmosphere? Or is that a no-no subject?
I don't think it's a no-no subject. I'm not aware of any papers that have shown a relationship there. So that's one of the things that I should have mentioned. I mean, one of the difficulties in sorting through all the data and the analysis, it's very easy today to write a blog piece or give a newspaper article. But the test of science, that's why IPCC is so important, these national assessments so important. Publishing in peer-reviewed, you put out what you think your best estimate of the observational data and your understandings of the models are. And you have your peers able to look at that, and if they come up with a better idea, it will show some substantial differences, and they could point out why it's different. And science moves on that way. And I think part of what we're hearing today is a concern expressed by some of so-called, I guess I would describe it as consensus science or herd mentality, and that is concern that, well, if some scientists all believe the climate is warming, they're just jumping on the bandwagon. But it could also be that they're actually all coming closer to the truth. They actually know that's true, and that's why they all believe it, or most of them believe it. And so I think one has to juxtapose our quest for testing what we know with there are some things we can be pretty confident about.
Okay, up here.
Hundreds of millions of people now go around carrying powerful computers in their pockets, and they travel all around the world, and I mean, many behavioral and social scientists now collect all types of data from smartphones. I wonder if there are any plans or projects that, attach sensors to smartphones to collect data in places that aren't currently covered.
Yeah, and I don't know of any in particular, but I do know citizen science has done some pretty interesting things with just simply taking pictures of phenomena we're unaware of, or being able to observe, for example, those pictures of some of those sites that I showed you. Without cell phones, that probably would never have been taken. Some of the things that citizen scientists have done, they've actually donated part of their computer time to run parts of computer models to get a better representation of natural variability, which has been very helpful. Other things that have been done, reanalysis, I don't know if Carrie's still here, Emmanuel, but reanalysis of hurricanes and tropical storms, looking at satellite pictures and trying to get an example of that. So there are things that can be done that can be quite helpful.
Let me ask a question to you, Tom. It seems, the issue for precipitation data is a pretty serious one. What do you see as the hope for the future to have much better knowledge of the spatial and temporal variation and ultimately of long-term trends in precipitation? Is there breakthroughs that are imminent, or is it just steady improvement?
Well, I showed the GPM, Global Precipitation Monitoring measurements, and having a set of satellites that really are measuring active measurements from radar, that's going to be a major step forward. I think it's too early to say how much of a big improvement that will be in measuring global temperature, because it has to be sustained, and one will need to look at that data and compare it and contrast it with, you saw some of those measurements with all the various ways of looking at precipitation data. It's really one of the underemphasized and discussed quantities, because it's probably, I think, one of the more important quantities, and some could argue more important than temperature in terms of what it does to the impacts on the planet. But we're in far worse shape in terms of understanding overall changes. So I'm not offering a great gleam of hope, but there is some hope with the GPM measurements.
Yeah.
Thank you. As I'm sure you know from a long career with NOAA, the primary users of this data at this point are not people intimately involved in collecting and analyzing them, but are like social scientists, policymakers, people in journalism, et cetera. Given the challenges with data collection at this point, what's the #1 caution that you would give to people like social scientists and policymakers who are trying to use precipitation and temperature data?
Yeah, I would say I'd be put it this way. I'd be cautious to make sure you understand the question you want answered with the data you have can really answer your question. And in some cases, it can do a remarkable job. So if you wanted to know, how much wetter this year was compared to a period in the 30s, you probably get a good idea, and depending on how accurate it needs to be, you can get that. If you need to know, is precipitation really gone up by 3%? Then you may be in some difficulty. So I think it really depends on knowing whether the data you're using can be appropriately used to answer the question you have. And that may mean talking to some specialists if need be.
Thank you.
Yes.
I apologize if you already addressed this, but I just recently in the past year, sort of the light bulb went on in terms of reading and so on. One of them was the Milankovitch cycles, which you may have or not done. And that seems pretty amazing to, have that kind of thing going on that might explain ice ages and stuff, regardless of the level of CO2 and so on. But the second one is, I read somewhere that one professor, I think Penn State, that one of the key things to kind of maybe get the public more into it in terms of the reality of climate change or global warming and so on, is the making the certainty around or reducing the uncertainty around the hypothesis that CO2 increase, the incremental increase over time is causing this global warming. It's like the driver. So many of them say that that's the driver. And around that, it's say, okay, great, there's a lot more CO2 in the air, so that's a greenhouse gas issue. But it's never really explained what the mechanism is around that blanket effect in terms of the individual CO2 molecules absorbing certain wavelengths and then emitting them after they're excited, emitting them randomly, and some of that goes back down and keeps it in there. Like, is there any visual sort of thing one could do with data to show people what that mechanism is? That, okay, I know we got car gas, CO2 going up, energy, coal, oil, and so on. All these sources of pouring the stuff into the air. What is that mechanism? And obviously, just a small quantity of CO2 gas has a ton of molecules in there. Is there some way to, use data to visualize what's going on there? And maybe they could see, okay, I get it. It's like a trap, and it is sort of, for us, a pollutant.
Yeah, no, I think that's a great comment. One of the difficulties, in fact, I would argue one of the gravest difficulties with carbon dioxide is you can't smell it and you can't see it. And so why did people, you could ask yourself, why did people get pretty excited with the oil spill in the Gulf of Mexico? Because every night on your TV, you could see the oil spilling out into the ocean. You can't see the CO2 spilling out in the atmosphere. And so I'm sure there's a lot of clever ways visually to make that point. I'm not aware of ones that I could tell you to go and look at, but I think it's a challenge for people to do.
Hello, Dr. Carl. I wanted to ask is, with all these data sets that are available out there and the requisite metadata that goes with them and all that kind of stuff, are you aware of any effort to try to unify these data sets under a single vehicle? I know that the oceanographic institutions collect lots and lots of data, and these days the tendency is that when you publish a paper, you're supposed to make those data sets available for the general public. And, collecting and curating this data and making it available, that's a big chore, not to mention an expense. And I know there's a project I've heard tangentially about called EarthCube that's basically trying to do some of that. But could you comment about these data sets since you're familiar with them in that task?
Sure. I always say it tends to be an unfunded mandate, and that is what we would like all scientists do when they go out and collect data or use data and process it is to save it in perpetuity. And scientists can do that to some degree in their own lab or their own institution, but what they'd like to do is, well, let's send it off to a quote-unquote permanent archive. Well, now imagine literally thousands of scientists doing analysis, all sending their data somewhere, which means the metadata, understanding it, you have to be able to document it, have a consistent format. There's some real cost there. And right now there isn't that long-term commitment to, there is a commitment to save the original data and some of the process data, but all of it, there isn't a commitment to do that. And that's one of the things that I think needs to change. I don't think there's an easy solution for it, because one can imagine we'll have to have some bar as to what we take on. One of the things we always thought when I was working at NCEI is if a data becomes inactive, sometimes it's worse than having no data at all, because people will take that and use it unknowingly, what processes were applied to the data, and end up with a result that's not what they might expect. So you really need active curation for this, and I don't think we've got a long-term commitment program anywhere.
Okay, we'll make this the last question. Thank you.
Given the sparse nature of the direct data collection in the Arctic areas, what can be done or is planning to be done to increase the number of sites for data collection in the Arctic?
There is some effort, particularly putting ice buoys out. Some agencies are involved in doing that. There is obviously efforts on measuring the Arctic today more comprehensively than we ever had in the past. However, you may not see these benefits until 10, 15, 20, 30 years down the line. If you recall, that climate reference network I put up had a growing set of stations in the Arctic and Alaska. It was the last place it actually went to, because it's really hard to keep measurements going where there's nobody around and it's hard to get to. I mean, really hard to get to. And so, but the point there is it'll take, you know, a number of years, even some of these efforts that are ongoing today. If you really want to see some changes, you got to be committed to doing that for 10, 20, 30 years.
Okay, with that, I think we should thank Tom for both the lecture and the answers.
Measurements in remote locations. Those are all important aspects, mysteries of really trying to understand this data that one has to consider. What I'm going to try to do to bring some reality to looking at this data is look through a couple of examples. One is constructing time series of changes in global temperature, and in particular focusing on this so-called pause in global warming that's been talked about for the last number of years, particularly since the IPCC 2013 report. And I also want to talk about measuring precipitation and its change, how much, how fast. We'll have some examples there and go through some of the issues. So I put this picture here, and I know some of the authors of these papers are in the audience. I know I saw Kerry Emanuel here, and I think he was part of one of the set of the co-authors. I put this on just to give you a sense of where we think we are when we talk about changes in temperature and precipitation. This diagram was put together by about 50 experts looking at whether or not we had more knowledge or less knowledge regarding a set of extreme phenomena that you see here. Everything from ice storms to heat waves, extreme precipitation, cold waves, and everything in the middle. So how much knowledge did we have with respect to our ability to detect changes from an assessment of 50 experts? And how well did we understand, if we saw the changes, the causes of those changes? Not unsurprisingly, there seems to be a relationship. Our ability to detect changes is related to our ability to better understand why those changes are occurring. So if you don't have much information of being able to detect changes, you don't know much about the causes of the changes. So we're going to talk about temperature, and certainly heat waves and cold waves are part of that, and precipitation. And you can see these are in the upper part of the diagram. Droughts, obviously, lack of precipitation, also related to the upper part of the diagram in terms of more knowledge and our ability to detect. So you'll see some of the problems that I'll talk about in these quantities, and so you can contrast to where we might be if we be talking about what do we know about changes in thunderstorm winds or changes in ice storms. Not very much in contrast. So I said we'd talk about temperature first, and obviously a lot of interest in global temperatures. Not surprising.
Well, I'd like to welcome you all to the 16th Annual Henry Kendall Lecture. It'll be presented today by Dr. Tom Karl. So I'm Ron Prynne, Director of MIT's Center for Global Change Science, which co-sponsors the lecture together with the Department of Earth, Atmospheric and Planetary Sciences, headed by Rob Vanderhilst, who I think is going to be in the audience somewhere. The Henry Kendall Memorial Lecture Series honors Professor Kendall. He was a 1990 Nobel laureate in physics, a long-time, very distinguished member of MIT's physics faculty, and a very ardent environmentalist. The Kendall Lecture allows MIT faculty and students and members of the general public to be introduced to forefront areas in global change science by outstanding researchers. Henry was a founding member and past chair of the Union of Concerned Scientists. He played a leading role in organizing a number of very influential scientific community statements on global problems, including the most well-known one is the World Scientist Warning to Humanity in 1992. That is copied in the brochure that you had in the second half of it, and the call for action at the Kyoto Climate Summit in Kyoto, of course, in 1997. Today's lecturer, Tom Karl, has had a long and very distinguished career in the National Oceanographic and Atmospheric Administration, known as NOAA for short. He was a senior scientist from 1992 to 1998. Then he became director of the National Climatic Data Center from 1998 to 2015, and then director of the National Centers for Environmental Information for 2015 to 2016. He's now seems to be very happy in his retirement, and that's why I think we were able to get him here. Tom Karl has certainly served the nation in what I'll call interesting times, in inverted commas. During his 1998 to 2016 term as a director within the NOAA system, the world witnessed the 12 highest global annual average temperatures ever recorded since 1880. Tom was responsible for delivering that dire news to a not always receptive Congress. Tom received his Bachelor of Science from Northern Illinois University, his Master of Science from the University of Wisconsin at Madison, and a Doctorate of Humane Letters from North Carolina State University.
Pretty quickly, but I do have a fair number of slides, but there's not a lot of content to some of them, so hopefully I can get through this and you'll be able to understand what point I'm trying to make here. But first I thought it would be important to give appropriate context because we're dealing with really the mysteries, wonders, and reality of climate data. And so here's a little cartoon for those of you who are fans of Don Quixote, and maybe I, in this presentation, consider myself kind of the Don Quixote, talking to Sancho Panza. Sancho, you consider yourself fortunate as I've deemed you worthy to accompany me on wondrous acts of chivalry, conquest. You'll see places of grandeur, noble adventures, deeds of bravery and courage beyond their wildest imagination. Sancho says, I believe everything you say, your worship, but right now you might want to buckle your saddles. It seems to be slipping off your high horse. So the point here is that while there is a lot we can do with this climate data, but as you see, there is a certain amount of reality to it. It is amazing today, if you consider what information we have to draw from all the different observing systems, from remote sensing, satellites, subsurface measurements in the ocean, land weather stations, upper air stations, radars, satellite imagery, and that's not to mention the data that comes from models. An enormous amount of information to pull together to try and make sense of what the state and changing state of the climate is. The wonders, it is amazing. Quality is remarkable when you think about the kind of measurements we're getting today, the variety of measurements, have you seen from that previous figure? The volume. I tried to make an estimate as how much of climate data is in the major centers around the world today. And an exabyte is not an exaggeration. That is a lot of data. Put some context on depending on how big your personal computer is. That's about 1 million personal computers. The measurements we have, active measurements, passive measurements. We've got international cooperation and data exchange, not to be underemphasized, because without that, we would not have nearly the amount of information we have today. We've got 24/7 by 365 and 366 in a leap year measuring going on. All this to not only predict what the climate's going to do, but to document.
Tom is a world authority on quantitative studies of climate change in the United States and globally, as recorded in a vast array of atmospheric, terrestrial, cryospheric, and oceanic observations from surface, submarine, airborne, and satellite sensors. He has his arms around huge amounts of data in his job over these many years. His many research accomplishments are described in over 200 peer-reviewed articles and books. He chaired the United States Global Change Research Program Subcommittee on Global Change from 2010 to 2016, in other words, through the Obama period, and was responsible for the delivery of the Interagency Global Change Research Plan, climate assessments, and annual reports to Congress. He was also chair or lead author of the first 3 of the U.S. National Climate Assessments and has testified many times on climate science before the U.S. Congress. He served as president of the American Meteorological Society and a member of its executive committee from 2009 to 2012, and he served as editor of its premier Journal of Climate from 1998 to 2000. Tom has also contributed substantially to major international organizations in climate science. He served as lead author, convening lead author, and editor on the first 4 Intergovernmental Panel on Climate Change Assessments, or IPC as they are called, from 1990 through 2009. He led the U.S. delegation that approved the 2014 5th IPCC assessment on the physical basis for climate change. Tom Karl is a recipient of a significant number of prominent awards, including the American Meteorological Society's SUMI Award, the Presidential Rank Award, 6 U.S. Department of Commerce gold medals, and the Helmut Landsberg Award from the American Association of State Climatologists. Tom is a fellow of both the American Meteorological Society and the American Geophysical Union. It's my pleasure to welcome Tom to MIT today. Title of his talk, as you can all see, is Climate Data, Mysteries, Wonders, and Reality. Welcome.
Thank you, Ron. And it's a very great honor to be here and to talk about one of my favorite subjects, climate data, to both those who participate in the Global Change Center for Global Change Science and with the Earth Atmospheric and Planetary Sciences program with the department. I have only several hundred slides, so I'll have to get through this, where we are now and how the climate is changing. So it's a remarkable set of assets that we have to draw from. Now, I said we've got great quality. We also have tremendous diversity in the quality. And so this then leads us to the reality and a lot of discussion amongst climate scientists as to how good is this data anyway. Here's an example. This is a reference, climate reference station that has been set up specifically for the purpose of measuring climate variability. I'll talk more about this and how we use it, but you can look here. There's a number of independent rain gauges in the middle of this double fence to try and protect the instruments from aerodynamics effect, the precipitation gauges from wind. It's got 3 aspirated sensors, platinum resistance thermometers, extremely good. But we also have many stations to draw from that don't have this high quality. And here's the worst example that I think we could find. This was a picture of a NOAA cooperative weather station. And you can see here's the cooperative temperature measurements being taken in this instrument shelter 5 feet away from this trash burn barrel. So the question is, well, how do you make sense out of these data? Can you really trust them given this disparity? We have issues of quality that relate to the calibration history of the data. So in other words, I want to know how those instruments have been maintained over the years. There has been changing in observing methods, the way in which temperatures, for example, are sampled or precipitation sampled. I need to know that. Changes in instrumentation. How good is the metadata about these types of changes? Can I trust it? That's also extremely important. The environment surrounding the measurement, is it changing over time? Has that burn barrel been there forever, or has it just been reintroduced in the last couple of years? How do I interpret the measurement, the meaning of the measurement? Is it in an urban environment? Is it in a rural environment? Is it in the free atmosphere? All important. And then, not to be dismissed, if I'm going to make measurements, do I have power available? Is it solar power, some way of making an active measurement instead of a passive measurement? Do I have capability of bringing power to my